All right, welcome back everyone to the third session of CoqPL. So our first talk is going to be from Yihan. She's going to be talking about some work she did during her summer internship at Livermore. And just as an advertisement, she's graduating. She's going to be looking for PhD applications, or she's on the market, or whatever the phrase is right now. So take it away, Yihan.
Thank you. Hello, everyone. I usually go by Yuki, and I'm an undergrad from Harvey College. Today, I'll present our work to verify linear algebra programs through equivalence. This work was done at Lawrence Livermore National Lab as a summer project in collaboration with Mohit, John, Matt, and Ignacio. They were all from Lawrence Livermore National Lab. Right. Scientific computing is changing fast. We're seeing big shifts in how computations are done, driven by new trends in hardwares. For example, we're seeing data compression floating point formats to deal with the cost of moving data around. And that was a huge bottleneck in traditional computing. We're also seeing a lot more reduced and mixed precision formats, especially in things like machine learning. And on top of that, there is a big push toward parallelizing computations on GPUs and FPGAs, along with a shift toward heterogeneous architectures. And those changes in scientific computing means that we need a new generation of numerical algorithms. But here comes a challenge. For the case where the new algorithms are a variance of the existing algorithms, how do we make sure that those new variants are correct and safe to deploy? And that's the key question that we need to address as we move forward. So the solution to this question is to prove the equivalence between the new variants and its classical counterpart. There are a lot of classical stuff that can be served as a ground truth of the correctness of the new variants. And the recent work published at PL'Di last year proved the equivalence between dense matrix vector product and sparse matrix vector product with different sparse matrix representations. So inspired by this work, we aim to prove equivalence between variants of a fundamental orthogonalization algorithms. It's the Gram-Schmidt algorithm. The Gram-Schmidt algorithm has two variants, the classical one and the modified one, where the modified one is more numerically stable. We picked to prove the orthogonalization algorithm because it is very fundamental in linear algebra, and it has a lot of applications. It's very important in machine learning, such as in optimization and regularization. Some other applications include cryptography, where they use the algorithms to orthogonalize the basis of a lattice for better efficiency and security. It's also being used in signal processing and noise reduction. So with the goal of establishing program equivalence between the classical Gram-Schmidt and the modified Gram-Schmidt, we proposed those three research contributions. We extended the MathComp library in Coq to include basic linear algebra theorems, and then we used this extended linear algebra libraries to prove the properties of Gram-Schmidt algorithms. And we finished the proof of the classical Gram-Schmidt by the time of this presentation. Furthermore, the library is a building block toward floating point reasoning and error analysis. So what exactly is the Gram-Schmidt algorithms? Well, it takes in a set of finite linearly independent vectors in some space Rn, where we call it V1 through Vk here, and then it outputs a orthogonal set that span the same subspace as the input set. And right here, we use the letter U to denote the output. So in other words, it creates a orthogonal basis from the input set. So we can take 2 dimensions, for example. We can see that V1 and V2 over here are the input vectors. They are linearly independent. And then we output vector U1 and U2, and we can see that they span the same space and they are orthogonal to each other. The algorithm accomplished this using the idea of projection. So by projecting V2 onto V1, it breaks up V2 into 2 components, and the component that is perpendicular to V1 is our result vector U2. And in math, projection is defined as some operation of dot product. So going back, Gram-Schmidt has 2 variants, where the classical one is very well defined in linear algebra, and you can find it in almost every linear algebra textbook. So the computer scientists took the classical version and then coded up and see that it is numerically unstable in floating points because of the running errors. Therefore, the computer scientists developed a new version called the modified Gram-Schmidt to reduce the errors. And we can see that right here. The modified Gram-Schmidt uses another iteration of projections of vectors to reduce the running errors. And then I can talk through the math a little bit more details. So in classical Gram-Schmidt, we take each vector one at a time and make it orthogonal to all the previous vectors. However, in modified Gram-Schmidt, we take each vector and modify all the forthcoming vector to be orthogonal to it. If we could take 3 dimension, for example, here we want to project V3 onto U1 and U2 to come up with the resultant vector U3. And then it's just simply subtracting the component that is perpendicular to V3, U1 and U2 right there. And then we're in modified Gram-Schmidt, we first project V3 onto U1 to create an intermediate vector right here, and then project this intermediate vector onto U2. So by iteratively projecting the vectors onto the orthogonalized vectors, it could reduce the running errors and then make it more numerically stable. So we can look at evidence for stability. Here is a study at UPenn. The orthogonality error was calculated for both the classical and modified version. We can see that as dimension k goes up, the error for classical Gram-Schmidt, which is shown in this middle column right here, quickly diverges away from 0. Well, the modified Gram-Schmidt the error of modified Gram-Schmidt stays relatively low. So with the goal of proving their equivalence, we also want to focus on stability and convergence. However, existing work doesn't fully address this. Where in Isabel, Hall, and Lin, they both only consider the classical version and does not consider numerical stability. Furthermore, in Lin, which is widely used to mechanize math, it uses a non-computable definition of classical Gram-Schmidt, thus we cannot extend the result to actual programs. So our work tackles this challenge by formalizing Gram-Schmidt and keep in mind the numerical properties such as stability, numerical convergence, and flows in the long run. So next, let's go to some technical details of how we actually mechanized Gram-Schmidt. Looking back at the definitions, we certainly need some definitions of vectors and linearly independence, orthogonality, and the idea of vectors spanning some space. The process of Gram-Schmidt also requires us with the definition of projections and dot products. We use the mathematical component library, aka MathComp, in Coq to develop the implementation. And MathComp has two sublibraries called vectors and matrix that's really helpful in doing this. Those libraries provide a lot of low-level definitions such as vectors and linear independence. However, it lacks definition of dot product and thus orthogonality. It also does not have higher-level theorems such as the basis theorem that are required to prove the correctness of Gram-Schmidt. Given this situation, we used MathComp to build toward a comprehensive linear algebra library that can help with the proof of Gram-Schmidt. The library starts with our own definition of vectors, which is defined as a column matrix, and then we define dot product and projections in the usual mathematical way. I don't have the time to go over our entire library, but here shows the dependency graph of the properties that was proved in the library. Here you can see that we proved the distributive property of dot product, some projection properties, and we used those more fundamental lemmas to prove more involved theorems, such as orthogonal decomposition theorem and the basis theorem. And there's one theorem that I kind of want to walk over this time is this theorem called products ortho, which is more formally known as the orthogonal decomposition theorem. So here's what the theorem states. It's very mathy, so I want to walk through the definition of the theorems. So we have a vector A and a set of vectors U0 to UN-1 in some space Rn. We conclude that A minus the projection of A onto all those V's, the result would be orthogonal to all the V's. We can imagine this as breaking up the vector A into components that is perpendicular to all the V's, and then by subtracting from those components, the leftovers must be perpendicular or orthogonal to the V's. And an equivalent Coq translation of the theorem is shown in the middle right there. And notice that here I have a little trick. Instead of saying that for any set of V's, the result hold, I made it stronger by saying, oh, let's fix the V's to be V0 to Vn-1. And then we consider a subset of them by only considering the V0s to Vk-1, where k is less than or equal to m. I do this trick to better fit this use case in later on proving Gram-Schmidt. And if the k just equals to m, then this is exactly same as orthogonal decomposition theorem in the Max textbook. And the proof of these properties requires dot product and projections, which are missing from the MathComp library. But with our newly created linear algebra library, we were able to successfully complete this proof. And I'm happy to go through the details later if anyone is interested. And this theorem was also added to our library later on, after the theorem is proved, to prove the correctness of Gram-Schmidt. So after we create the library, we're now ready to prove the correctness of classical Gram-Schmidt. Here shows the dependency graph of proving the correctness of Gram-Schmidt, and we see that it uses a lot of properties established in our linear algebra library, and all those arrows pointing to is a lemma that's unique to our own library. And let me zoom in on this lemma right here in the middle. This is called non-zero result vector helper. I named it myself, and this is the key helper lemma to help us develop the correctness of Gram-Schmidt. And here's what it states. It also gets really messy. So let me walk through. So let this set of v's, v0 to vm minus 1, be some vectors in Rn, and they are linearly independent. So they are the input to our Gram-Schmidt algorithms. Let all the u's, u0 to vm minus 1, be the result of Gram-Schmidt. And we conclude three things. First is that all the u's, all the result vectors are non-zero, that's the first one, and they are pairwise orthogonal, that's the second one. And furthermore, the third one is that all the v's span the same space as all the u's. This almost comes directly from the definition of Gram-Schmidt in classical math textbooks. I added the result of all of them being non-zero as an additional conclusion to help me reason about this proof. And the inductive hypothesis of this proof would be that we assume for a certain k that the first k of all the u's holds for these properties. And then for the inductive step, we want to prove that it holds for k plus 1 as well. So to prove this inductive goals, we have three parts that we need to prove. Let's see. There we go. OK. First is that the k plus 1 vector, meaning the uk is non-zero, and that it is orthogonal to all the previous u's, and that it spans the same subspace as the first k vector, as the first k plus 1 vectors in the input set. So to prove the first one, that uk is not zero, I break it up into, I've expanded out into its formulas, and then to prove this, I used both the lemmas in our own library and also some already established quite good lemmas in MathComp. And to prove the second part, I used orthogonal decomposition theorem, which is the one that we just saw in the previous slides. And for the third one, we actually need to use the basis theorem right here. So yeah, we're able to successfully complete the correctness of classical Gram-Schmidt using our own library, and we are in the process of proving the correctness of modified Gram-Schmidt. A lot of helper lemmas in the classical Gram-Schmidt can be used here, and there is an additional lemma that is unique to modified Gram-Schmidt is already proved on pen and paper. This basically saying something about properties about this intermediate vectors that is unique to Gram-Schmidt. And last but not least, we could use the orthogonal decomposition theorems together to complete the proof of modified Gram-Schmidt. And the proof structure of those two versions essentially established so that the equivalence one will be very simple by just doing an induction on the number of input vectors. And after we do that, we could successfully close the exact equivalence of those two algorithms in real numbers. We're imagining our work to be contributed directly into the MathComp library, mainly the vector library, because we use a very similar definition of vectors. And we hope that our library could be established for proving other basic linear algebra theorems that utilize projections or orthogonality. For example, people can use our library to mechanize some ODE solving techniques that heavily relies on linear algebra. And our library can also help with the mechanization of QR decomposition, which is an application of Gram-Schmidt algorithms. And for a long-term future work, we're thinking that there could be three possible ways. First, we could reason about floating point programs, and this extension would require first adapting the equality constraints of our lemmas to symbolic bounds, because in real numbers, two vectors being orthogonal, meaning their dot product is zero, but then that's not true in floating points because of running errors. And second, we could extend our equivalence result to reasoning about low-level HPC programs by using separation logic such as Iris. And our final direction could be extending recent mechanized relational equivalence framework, such as LGTM, with support for floating points and proof rules for common linear algebras to include modular reasoning. And that would significantly automate the process of constructing floating point error bounds. So in conclusion, we extend our MathComp library to include some linear algebra theorems, which we later on used it to prove the correctness of Gram-Schmidt. And we expect it to be extended to handle floating points and error reasonings. I'm very grateful of our results so far, but the process is not very smooth. First of all, it might be a surprise for you all, but mechanizing math is actually quite hard because of a lot of missing pieces in the libraries. In addition, formalizing software is also challenging because essentially missing those building blocks that's missing from the library enable us to create our own new library of linear algebras. And so Gram-Schmidt is a very fundamental algorithm in linear algebra, but we expect it to be more complex when proving more complex and more involved algebras. And as a learner of Coq myself, I spend a lot of time trying to prove some common sense results. Therefore, I ask for more automated theorem proving tools. And I use LLMs a lot during my proving process, and I'm happy to explore ways of how LLMs could help in automating theorem proving. Last but not least, I have mixed feelings about floats, but it is because it is not as exact as reals. But I'm grateful to have the Coq library called Flock and MathCom to help me reason about floats and reals in Coq. Thank you for your time, and I'm happy to take any questions.
We have plenty of time for questions. Is there any questions in the audience? We got one right over here.
Thanks. Is that working?
Oh, it was working.
Yeah.
Now it's not.
I'll just. How much of the geometry you built depends on? Or at the bottom.
Okay, yeah, just to repeat, the question is asking whether how much of the proof relies on the definition or the representation of vectors. Is that right? Yeah, so we define vectors in a pretty standard way, I would say, is being defined as column matrices. Right here is a column vector. And that by defining it that way, we could use the matrix library in MathCom and also the vector library in MathCom to reason. So I would say the proofs definitely relies on this representation. I would say this representation is pretty standard. Yeah.
What is the representation?
In matrices, I don't remember it to be iteratively defined. I think, yeah.
From the product. The wrapper on top.
Yeah, I feel like because there's a lot of lemmas in vectors and in matrix that we can directly use, so I didn't have it's not heavily relies on how it is defined because there's already many lemmas help me to iterate with the representation. Yeah.
Yes, I'm wondering why you chose to base your linear algebra on the matrices as opposed to the vector library, which is basis independent.
Sorry, could you repeat your question?
So there are basically two linear algebra libraries in MathComp. One which is representation dependent, which are the matrices, and one which is basis independent, which is the vector library.
Yeah.
So I'm curious why you chose to work with the matrix library rather than the vector library, which is a little more abstract.
Yeah, we actually use a lot of lemmas established in the vector library. We use it a lot. But then one reason that we didn't use it because there is no definition of dot product in the libraries. I
Obviously,
mean, it is
you could add it, right?
It's implicitly defined used by the transpose of one vector times the other vector in the matrix library. But then because it doesn't have the definition of orthogonality, which heavily depends on dot product, so we didn't really use the vector library. And also vector library.
I understand, but you could have built on top of it as opposed to trying to hook yourself to matrices, which are a little more lower level.
I think the vectors defined in the vector library uses the column matrix representation.
Internally, but it doesn't.
Yeah.
But the interface doesn't expose it.
Right. Yeah. I mean,
there's actually an example of this in the math comp library, but sort of further down. The theory of characters actually develops the whole theory of dot product and orthogonality. It just does it only for class functions because we're kind of goal oriented. But
right.
You could have used that as a basis for rolling out your own while being staying above the layer of the matrix.
Right. I think we could talk later.
Yeah, maybe we can take this offline.
I'm curious about that library.
The next speaker, is the next speaker in the room? Yeah, can you come get set up? We have time for maybe one more quick question.
Oh.
Or not? In that case, let's thank Yuki once again.